Hello, everyone. Welcome back. This is the second talk of today. Professor Xiaodong Xu from University of Washington will give us a talk on magnetism, interaction, topology, intrinsic condition model, dichalcogenide, part 1. Let's give a warm welcome to Xiaodong.
Okay, I would like to thank the organizer for the invitation and to speak in this summer workshop. Actually, this is my third time here. So it means I did a good job in the last 2 times. And hopefully I will be invited back again. All right. And let me just, since I know there's a lot of students here, and I would like to just advertise University of Washington. It's in a beautiful city of Seattle. And this is a picture I took with my phone and at the Gasworks Park, which is about less than 1 mile away from the campus. So from here we can see right the skyline of the cities. And the first, this is the Space Needles, and just behind there we have the stadium for Seattle Sounders, for Seahawks, etc. Just back there. And we also have the first Starbucks coffee, right? We know Starbucks is actually the headquarters in Seattle. So this place is just near the marketplace in the downtown Seattle. And we also have a beautiful love stories. And if you look for romantics, you can come to Seattle. And the Gasworks Park itself it's a nice place for host their parties. So I don't know if you can see this here, just a second. So this is actually the annual barbecue party I held just at the Gasworks Park 2 weeks ago. You can see a lot of people here. And these are the students actually graduate this year, like 5 students plus 2 postdocs. So it's a big turnaround. So what it means is that there's opportunity in my lab. If you're looking for postdoc positions, please contact me. So not only we have these beautiful parks, etc., and at the UW we have many centers. So here I highlight these Mercek Center. We have these AMAD, which is this one. AMAD is the center from NASA funded, study optoelectronics. We also have several centers to study quantum effects and as EFRCs and MURI, etc. So it's very active research environment. One thing I will highlight is Thales Institute of Quantum Matters. Right, we all know David Thales. He got Nobel Prize at the 2016, right, with Duncan's and Costless. So this is for the theoretical discoveries of topological phase transitions and topological phase of matters. So we established this this institute after Thales, and this institute has very active. For example, right, we host annual these workshops. So this is the one we just hosted in the past winter, right? You see a lot of it's about new developments in fractionalizations. You see a lot of participants, and many of them actually from Princeton. So one exciting opportunity is that by this fall, we can launch a David Thales postdoc fellowship or Thales fellows. So we're really excited about these opportunities to recruit the best talent from the world. So again, right, if you're interested, please, right, you can look out for these opportunities. Okay, so now we're going to talk about it. We're going to talk today, right? So the topic I talked to you today, actually, I think it has deep connection to technologies. For example, right here, I highlight the discovery of the transistors back to 1948, right? These are 3 gentlemen at the Bell Lab. They discovered these transistors using germaniums. This actually leads to the revolution of microelectronics, right? We know that from these vacuum tubes to transistors, now we have these portable cell phones, etc. And the development technology doesn't stop here. Right. Here I stole this roadmap from TSMC, where they highlight the development of transistor. Right, a few years ago, it's still 28 nanometer. Now we're already pushing to 5 nanometer, and TSMC already in the production of 2 nanometer transistors. So during the pursuit of technologies, right, there's something really beautiful happen in the condensed matter physics, which is discovery of this quantum Hall effect. So back to late 1970s, right? Von Clinton, he got these silicon transistors. Then he started to study the transport properties of these 2D electron gas, right? So we know that when you apply a large magnetic field perpendicular to these 2D electron gas, then when he measured the Hall resistance, and he found out these plateaus. And one simple way to understand this is in the Hall conductivities, right? It's proportional to integer c, and the times in the unit of this e square of h. So we now know this as integer quantum Hall effect. And a couple years later, right, the sample actually improved. What it means is lower the disorder and the mobility is enhanced. Then the electron correlation effect becomes important in such systems. This leads to the discovery of a fraction quantum Hall effect. So give me just a second. Somehow the slides didn't show here. I apologize for that. But you can imagine, right? The quantization is in the fractional values. So we know that in these systems, well, one way to understand this quantum Hall effect, right, I stole these actually from Wikipedia, right? It's really beautiful, showing that when you apply magnetic field, Landau level actually forms in these 2D electron gas. So whenever these Fermi level, right, cross these Landau levels, and you will see these, right, you will see the enhancement of connectivity. Then when you're in the middle of these energy gaps, you see these plateaus. So this is one way to understand the formation of a quantum Hall effect due to these the formation of Landau levels. Yeah, here's the slides I was looking for, and I come back again, but you already know what it is. So basically, the key idea is that when you're partial filling of Landau levels, and the interaction of these carriers will open up these quasi-particle gaps that lead to this fraction quantum Hall effect. One remarkable thing about all these quantized Hall effects is that they're coming from a dirty 2D electron systems, right? Here I show you this optical image of the gallium arsenide sample used for the first realization of this fraction quantum Hall effect. And you can see the sample itself is on the order of centimeter scales, and these contacts you see on the surface, right? It's not as pretty as what we can do now, use standard electron lithographies. And also there's a lot of dust or dirt on the top of the surface samples. So with such a dirty condensed matter system with 10 to the 23 of electrons inside, somehow all these electrons can behave in a collective manner and give rise to these quantized Hall effect. So this reflects that something amazing happened in the system. And now we know this amazing thing is called topologies, right? Just give you a very quick overview of topologies, which means is there's some kind of topological invariant in the system to describe the global property of the objects. And these topological invariant, it won't change by local perturbations. So here I use these number of holes as a topological invariant to describe these objects. And we can see there's a golf ball and there's a cup, right? Both objects, they're physically different, but they can transform one to the other without breaking apart. In this case, the topological invariant is a 0. Then now we know that if I have a coffee mug and with a donut, even though both are very different objects, right? One is cup, the other is, well, for breakfast, but they belong to the same, they have the same topological invariant, which is a 1, because both of them has 1 holes in the systems. We can continue this, right? Of a pair of glass, you have a topological invariant 2, and you have this appraisal with a topological invariant 3. And so what David Solis realized is that actually in the electronic systems, there's a topology invariant can be used to describe the electrical conductivities. So that leads to the quantized Hall plateaus in this quantum Hall effect. So here's the work from David, right? Went back to 1980s. So in the first paper, right, was quantized Hall conductance in a two-dimensional periodical potentials. In this one, David and his colleagues, right, derived these TK-Kn formula. So the essence of these formula is that they found a chain number which used to describe the conductivity of the Hall conductivity of systems, is that proportional to the integral of the Barry curvature of the first Brownian zones and anomalous by 2 pi. So these chain number actually describe the quantized conductance in the systems. And a couple of years later, in a second paper, and Derry and his collaborator actually extend these TK-Kn formula into the situation including many body interactions and also substrate disorder. So what they found is that in this case, right, the fraction quantum Hall effect, right, these can also be described by these formulas. So basically, this chain number not only is integer, but it can also be a fractional number. So the essence of this paper, right, these two papers, is basically saying that this quantized Hall effect has these topological origin of the system. There's a lot of interesting things about these fraction quantum Hall excitations. And one of the interesting properties is the physical representations for anyons. So just a quick overview what anion is, right? It's a strange particle in the two-dimensional systems. So imagine, right, in a 2D systems, we have two indistinguishable particles at the position R1 and R2. Then the wave function can be written down as a psi, just R1 and R2. Now what we're going to do is we're going to exchange the positions between these two particles. Now the wave function becomes psi, the R2 and R1, okay? From quantum mechanics, we know that the wave function of these, of these two wave functions can be connected by this formula with a phase factor e to the I theta in the front. So we know that for these particles, right, we can have a fermions, we have bosons, those are the two fundamental particles. And that means theta either equal to 0, which describes a boson, or theta equal to pi, which describes a fermions. And in the two-dimensional limit, what's changed is that the theta actually can be a rational fraction of a pi. That's gives rise to the name of anyons, given by Frank Wilczek. So initially, the idea of anion is sort of an abstract concept, and people are looking for is any kind of physical system, right, can realize these anions. It turns out that the discovery of these fraction quantum Hall effect gives rise to a physical system to study anions. So here are the two theory papers to establish these connections. One is from Bert Hapling, the other from Frank and his collaborators. So what they show is that these fraction quantum Hall effect actually has these fractional statistics and obey these anion exchange statistics. So later on, when the sample quality improved, there's new fraction quantum Hall states being discovered, such as even denominator, 5/2, etc. So with these new states, the theorists also proposed that there's a non-abelian anions associated with certain fraction quantum Hall states. So anion is not only fundamentally interesting, but also is can be practically useful. So this is the paper from Kataev, right? He describes that how we can use anion to realize fault-tolerant quantum computations. Right now we know that for quantum computing, one of the challenges is the decoherence of these quantum bits, or qubits, right? Because qubit is easily coupled to the environment and to lose the decoherence. So, but if we can find a qubit which is immune to the environment, then there's a good chance, right, to overcome these quantum errors and to build these quantum computing. quantum computers. So this is what the Kataev pointed out, is that you can use these anyons to realize these quantum computers. So the key concept why you can do this is, here I highlight a review paper, right? Topological quantum computations from basic concepts to first experiments. So all these diagram what is showing here is that for a anion, which is described by a reduced Hilbert space, what it means is that to describe these quasi-particles, right, the degree of freedom actually reduced to only positions. So therefore, if you want to change the wave functions, so you have to swap the positions of particles, okay? So as I show here, all these diagrams basically showing how you can change the positions of quasi-particles called abrading operations. So what it means is that all these particles, the wave function of anions, right, is actually immune to local perturbations, which is immune to these quantum decoherence. Because in order to, if you want to modify this wave function, the only thing you can do is to swap the positions, which is harder to do, right? So that's the basic idea behind why you can use anions to realize these fault-tolerant quantum computations. So there's a lot of proposal there, how you can realize these non-abelian anions for these purpose. Here I highlight the idea which you can interface a superconductor with fractionally quantized edge states. And once you have that, there's possibility to realize one type of non-abelian anion called parafermions, for examples. Then there's a possibility to do these fault-tolerant quantum computing. But there's a challenge, right? To do this is you need to find a robust edge states and can interface a superconductors, then look for these non-abelian anion signatures. Here's a work I highlighted from Phillips' group, right? They made an attempt by interface a superconductor here, which is this blue stripe, and on a graphene to the electron gas systems. So in these experiments, they observe these called CARS, which is crossing angle reflections across these superconducting stripes. But there's no signature of these non-abelian anions. I think the challenge is that because in this particular experiment, right, if you want to realize this fractional quantum Hall effect, you need to apply high magnetic field. In this measurement, they use 10 Teslas. So when you have this high magnetic field, you create a vortex in these superconductors, which is actually kill these non-abelian anions. So with that, you see that the challenge, right, to the current proposals, right, by interface superconductor with fractional edges. The challenge is that for fractional quantum Hall effect, right, it's a fragile features. You need very low temperatures, and also you need a high magnetic field to realize this fractional quantum Hall effect. But we know that the superconductor actually doesn't like magnetic field. So to overcome this challenge, we would like to realize this fractional quantized Hall effect at higher temperatures and without applying magnetic field. So that's what I'm going to talk to you today, right, is fractional quantum anomalous Hall effect. To realize this FQH effect, we need a strong interaction in the systems, right? We need a band to be topological, and we need to spontaneous break time reversal symmetries, which is spontaneous magnetic order in the systems. So there's a lot of ideas along these directions. This one I'm going to highlight is from Duncan. Right? Duncan proposed this toy model, now we know as a Holden model, how you can realize these quantized Hall effect, but at zero magnetic field. So here you have these honeycomb-like structures, and by introducing these imaginary nearest neighbor hoppings, and it's possible to realize this quantized Hall effect. As wrote in Duncan's paper, right? You can see that the model, right, presented here is unlikely to be directly physical realizable, means a toy model, but it shows that these quantized Hall effect, right, can be realized in the presence of magnetic orders, right, in a quasi two-dimensional systems. So basically saying that we need a strong interacting basically we need a topological system, but with a spontaneous time reversal symmetry breakings. And so built on these Duncan's models and at the early 2000s, Charlie King and Eugene Milley, they introduced these spin orbital coupling into these Hodan models. Now we know as King-Milley models. So once you have these spin orbital couplings, what King and Milley shows that you can realize these quantum spin Hall effect. The model they do is built on graphenes. Then in such a systems, right, you can consider as a 2 copies of Hodan model, right, with spin up and spin down. Because in Duncan's model, it's a spinless models. There's no spin orbital coupling. But in King-Milley's model, because introducing of these spin orbital coupling, now you have 2 copies of Hodan model. So you can imagine that if we can break the time reversal symmetry of the system, basically lift the degeneracy between spin up and spin down, then you go back to Hodan model, then there's a chance to realize these quantize the Hall effect, but without applying magnetic field. This effect, now we know as a quantum anomalous effect, was first realized in this magnetically doped topology insulator, right, by Cui Chang, and when he was a student in Qi Kun's group in China. So what they do is that they dope these 2-dimensional topology insulator with chromiums. Then they observe that the zero magnetic field, right? The key is the zero magnetic field. They found these how resistance is quantized at a 1, right, in a unit of h of these squares. And at the same time, if you look at the RxX, right, RxX actually it is strongly suppressed, basically close to 0. So the hallmark of this quantized Hall effect, the zero magnetic field, is that you need quantized Hall resistance with a suppressing longitudinal resistance, which is RxX. So we're going to go back to these. So the effect I talked to you was basically it's an analog of integer quantum Hall effect, the zero magnetic field. Then the next step is a possible way. How can we realize this fractional version of this quantized anomalous Hall effect? And there's already a lot of models, right, along these directions. For example, right, here I highlight a paper from Laughlin. He studied this fractional quantum Hall effect in these spin lattice systems. So there's also models of a fractional quantum Hall plus periodical potential, basically in a lattice systems by Nick Wright. At the early 2000s, when these cold-atom quantum simulator becomes really powerful, then there's a lot of theory proposals how you can realize this fractional quantum Hall effect in an optical lattice system. But all these models I talked to here, you actually requires a specific time reversal symmetry breaking, for example, by magnetic field. And the zero magnetic field version of this fractional quantum Hall effect was firmly established theoretically at the 2011 by several papers. But the key idea is that, right, as I already mentioned to you at the beginning, we need topologies, we need strong electron-electron interactions, and we also need spontaneous time reversal symmetry breakings. To realize all these ingredients, we need a flat chain band. Okay, so once we have flat chain band, then it's possible to realize these fraction quantized Hall effect, the zero magnetic field, or I call FQH, or the state itself, you can also call as a fractional chain insulator. So there's a lot of material system being introduced and trying to realize such effect. So the material system I talked to today is based on these Moiré materials. Right, we probably, we all know that, right? Moiré means, imagine here, I use graphene as examples. So I have 2 sheets of graphene stacked on top of each other. And once we add a little rotations, then the interference of these 2 crystals, right, give rise to these superlattice in the real space. Another thing about these synthetic superlattice that you can control the lattice constant, right, just by control the twist angle. You can also control the doping of the system just by electrostatic gating. That's a nice feature of 2D materials, very easy to control the carrier densities. So you can see that in such a system, right, the lattice constant and the carrier densities both can be controlled in situ. Not a trace angle, but for most of the labs, but I'm going to talk to you one method that actually can control these in situ. So here I'm also going to introduce you the concept of filling factors. So the filling factor, what I mean here is the number of carriers per mole unit cells. You can think of it like mole densities. So this is what I was talking about. That like Shahar Ilani's lab, they introduced a way actually you can control a twist angle in situs. They call it quantum twisting microscope. So the beauty of the system is that they put a 2D materials. One of them is as a substrate. The other one is attached to a tip. Then by rotating the substrate, actually you can in situ control the twist angle between these two materials. So they demonstrate this idea by using twisted graphings. So what I show you here is the band structure. They measured, use such a system because when you use twisting microscope, they measure the tunneling current between top surface and bottom surface. At the same time, they can control twist angle, which give you the degree of freedom in terms of momentum space. So you can think of this twisting microscope as a combination of angle resolved measurements, which is momentum resolved, and plus the scan tunneling effect. So one of the powerful things they demonstrate is that not only you can measure the band structure, but also you can push the tip to the samples, which is equivalent to applied pressure, so you can control the band structure in situ. Okay. So with this introduction, I will just like to give you a comparison, right, of these the solid state system, which is a Mori quantum simulator, to this cold atom quantum simulator. Right, in a cold atom, right, if you found the community, what you know is that they apply multiple laser beams, and the interference of these laser beams will create the traps in the real space. And the traps, the dimensionality, right, usually is on the order of micron scale because that's limited by the wavelengths of the light. But in these solid state Mori simulators, it's very much like the cold atom quantum simulator. The difference is that the lattice constant I talked to here is on the order of 10 nanometer, so much smaller. And you can think of the interactions in solid state system is stronger. So it means for many phenomena, one the static can go much higher temperatures. And another, I think, advantage of solid state system is that it can make as a device, then you can really control the physical parameter in the system, right? Because all the materials, they come with a certain, they have their own personalities, right? For example, you can pick a material with a strong spin out of couplings. You can pick a material which is already topological or which is already magnetic. So this gives us a lot of freedoms, right, to create these solid state quantum simulator. So I think these two systems, which is complementary to each other, right? Because for cold atom, you can precisely engineer Hamiltonians, and the system is really clean. For a solid state system, right, it's dirty, but it gives a lot of tuning parameter in the system and with stronger interactions. So with this Mori system, what the Alan McDonough shows that actually you can create a flat band using graphing as an example. So he introduced this magic angle around 1.07, 1.09 degrees. And this magic angle, right, what I show you here, right, is the band structure as function of twist angles. So basically, at this 1.06, this magic angle, the band become really flat. So using such a concept, Pablo's group at MIT, they realized these superconductivities in such a systems. Right? They show that the magic angle twisted by the graphene, the emergence of the superconductivities. And this is really exciting discoveries, basically to kind of excite the whole field. And we have a very exciting field of Mori quantum materials looking for all sorts of different phenomena. So one of the exciting phenomena is to look for topologies in magic angle graphene systems. Right? Here I highlight the field theory works, and it shows that you can use this graphene system, which becomes already flat band, right? And the theory work shows that it's also possible to realize topology of the systems. You can introduce strong interactions, topologies. It's possible to realize these fractional chains later. In experiments, what the people has done is that they observe these orbital magnetism in the systems, right? This was first realized by Stanford group. Then build on this group, Andre Yang also observed these quantized Hall effect actually at the zero magnetic field. So basically, these quantized quantum anomalous Hall effect is now realized in match angle twisted graphings. But there's a challenge of such a system, right? Just like any 2D materials devices. It's really difficult to actually to engineer the same system and to make these phenomena repeatable. So that's an open challenge in the community. In addition to these integer quantum Hall effect, the zero magnetic field, there are also exciting progress in this fractional version of these states, we call fractional translator. So there's two works I'm going to highlight here. One is the Mori system formed by bilayer graphene with hexagonal nitride from Andre Yang's group at the Santa Barbara. So when the magnetic field is above 30 Tesla, so the observed states behave like a fractional translator. Then there's a second work I mentioned here is from the collaboration with Pablo and also Amir Yakovi at Harvard. They use these match angle twisted by the graphene, and they found out there's a fractional translator state with magnetic field above 5 Teslas. Okay, so all these shows, right, there's a great promise to use these twisted materials, 2D materials or Mori system to search for these fractional quantized Hall effect. So the work I show you here, right, you still need a magnetic field. So the challenge is how we push to zero magnetic field. Okay. And so the system I talked to you today is about the twisted MOT2 bilayer. So last year, we observed these fractionally quantized anomalous Hall effect or FQH in these twisted bilayer MOT2 systems. So I give you a summary here, right? So far, we have observed these high temperature quantized anomalous Hall effect at chain number 1, right? And also observe several fractional translator states. So these two states I highlight with these red fonts is a new state we just recently found, and still, I think it's there, but we still need a bit more measurements to firmly establish it. So the system I talked to today, the twisted MOT2, actually is quite robust. And so far, right, the phenomena has been observed in many groups in the field. Here, I just summarize all the experimental papers so far. In addition to these twisted MOT2, you may already heard from Long, right? They also observed these fraction quantized anomalous Hall effect in these multi-layer graphenes. And I think a couple of months ago, right, is the FQH effect also reproduced in multi-layer graphene by a group in China. So I would say that so far, right now, we have two material systems to study these FQH effect. One is twisted MOT2, the other is multi-layer graphenes. And I will not be surprised if the third system or fourth just appear in the near future. Okay, so what I'm gonna do in the next, the rest of these first lecture, gonna focus on these twisted MOT2s. So first, I would like to introduce you this material system, which is it's a transition metal dichalcogenides. So what I show you here, the crystal structure from a monolayer, right? Once you look from the top, it's a hexagonal lattice structure. And each of the corner of the hexagons, right, you have one is metal atom, the other is chalcogen atoms. So these two atoms, they break the inversion symmetry of the systems. This broken inversion symmetry give rise to these valley-dependent physical properties. What I mean is that the barrier curvature at these two valleys, they have opposite signs. And also the valley magnetic moment has these two valleys, K minus K, they also have opposite signs. So this valley construct physical property, right, give rise to many interesting phenomena in these TMD systems. One phenomenon I'm going to talk to you today is called valley-dependent optical selection rules. So as I highlight here, right, with one valley, for example, minus K, they actually couple to sigma minus polarized light. Sigma minus, you can think of as a left circular polarized. And then there's another one, which is sigma plus at the plus K value, which is coupled to right circular polarized light. So it means we can use the polarization of light to individually address these valleys. Now, you take a monolayer TMD and you cut into half, then stack on top of each other, but in the same orientations. In this case, we call A stacking or rhombohedral stacking. Then you add a little twist. Then we have these twisted transition metal dichalcogenides bilayers. So in these A-stacked bilayers, within a single more unit cells, there's two energy degenerate points. One is I call B here, the other is a C. So B is with metal atom on top of oxygen, and the C is actually a oxygen atom on top of metals. So these two are energy degenerate in the systems. Then you can see that, right? With these two Mori sublattice B and C, we found these honeycomb lattice here, all right? So this honeycomb lattice. Now it looks somewhat like a Duncan's model, right? And so it's pointed out by Alan McDonough is that in these twisted MOT2 bilayers, right, the top of flat band, the top of a valence band, actually it's a flat band and also topological. So what Alan pointed out is that I'm going to talk a bit more, just next slide, is because of these twisted systems, these layer degree of freedom, you can consider as a pseudo-spin, called layer pseudo-spins. So these layer pseudo-spin degree of freedoms give rise these Kim-Lee models. So we're kind of motivated by this work, basically showing that in twist MOT2, we have a flat chain band, right? So let me just walk you through the basics of why we get these Kim-Lee model in such a systems. Is that we look at the electrons equations motions. Here I write down, right, with positions and with crystal momentums. So the key is to look at the right-hand side. If we look at the equation for the position, on the right-hand side, we have these k dot cross omega k. K is a crystal momentum. Omega k is the barrier curvature in the momentum space. So in this case, this barrier curvature in the momentum space equivalent to these pseudo-magnetic field. So this term gives rise these anomalous velocities. And that's the phenomenon we usually know as this Wiley-Hall effect. Now we look at the second equations, right? Is on the right-hand side has r dot cross omega r. So r dot here is a position, right? It's a velocity basically, and we know that from classical, right? We know that you have velocity and a cross product of magnetic field that give you a Lorentz force, right? That's give you the usually Hall effect. But in this case, omega r is the barrier curvature in the real space, so you can think of another pseudo-magnetic field. Then this term actually give rise to this anomalous Hall velocity in the real space at the zero magnetic field. So this will give rise these anomalous Hall effect. But for most crystals, it's a homogeneous crystal. It's periodic, right? So what it means is this barrier curvature omega r in the real space vanishes. So this term we usually ignore in the equations of motions. But however, the situation will changes in the Mori superlattice because in the Mori superlattice, actually there's periodical variations with these atomic registries, right? So this gives rise to these barrier curvature in the real space. One way to think about this, right? So we have these two we have these two sublattice, B and C. So B, as I talked to you, right, it's a metal on top of oxygen. So you can think of pseudo-spin pointing up. And the C is oxygen on top of metal, right, which is pseudo-spin pointing down. So imagine if you're an electron, you're going to work from this point B to point C with a pseudo-spin pointing up to pseudo-spin pointing down. Then the pseudo-spin must rotate, right, from up to down. So if you're rotating in a two-dimensional space, then you'll get these layer pseudo-spin skirmions. So this gives rise to these barrier curvature in the real space and these pseudo-magnetic field. This gives rise to these Kim-Lee models. And that's just a theory. And very recently, my colleague, Matt Yankovich, he actually observed the signature of this layer pseudo-spin effect using scan tunneling, microscopy, and the spectroscopies. So here I show highlights the two pieces of results. In the middle, right, this panel I show you here is a topography image of this traced MOT2 bilayers at the 2.75 degrees. And then you see these bright spot represents the high symmetry point in these Mori superlattice, which is the metal on metal, okay, M point. Then you see these little triangles here, all right, and which is MX and XM I talked to you. Then on the right-hand side, this is the image that states from the K-valley flat bands, basically top of K-valley bands. And in this case, now you can see the denser states actually indeed localized at the MX or XM, right? Yeah, let's see. So you can see, anyway, so yeah. My laser pointer doesn't work well, but as I highlight here, you have MX and XM. Those are the denser states. So this shows you that indeed, right, we have these two pseudo spins. One is pointing up, the other is pointing down. So now we have such a system. The first question I want to address is whether we have a spontaneous magnetisms, okay, or ferromagnetic orders. So to measure ferromagnetism in a system, I'm going to introduce you the technique we use. It's called magnetic circular diagrams. So what we do is we shine circular pulse light, right, to the sample. And this polarization is modulated between left and right circular polarization. You can think of left-handed, right-handed, modulated. Then what we do is we measure the reflection, right, the different optical reflection difference between these left circular polarization and the right circular polarization, right? That difference we call circular diagrams. Then in particular, we measure these circular diagrams as function magnetic field. So the example I show you here is these MCD measurements as function magnetic field of a monolayer chromium triodide, which is a 2D magnet. So you can see that, right, in this curve, I have orange and green. So orange means the magnetic field is sweeping up, and the green means magnetic field sweeping down. So you see a hysteresis here, okay, in the MCD signal. So this hysteresis represents that ferromagnetism in the systems. In this particular case, we do polar mode. What it means is the spin actually pointing other planes. So we're gonna go back to such data very often in the rest of my talk. So the key message is whenever you see a hysteresis, you know there's a ferromagnetic order in the systems. So I just want to emphasize, by just seeing circular diagram doesn't mean you have a ferromagnetism, okay? Because there's a lot of phenomena that can give you a circular diagram. For example, like sugar. If you just get a sugar water, right? It also has a circular diagram, but doesn't mean it's ferromagnetic. So in order to see ferromagnetism, you must sweep magnetic field for this particular technique. You want to see hysteresis. So that's the first generation example we measured. So what I show you here, right, we have this twisted bilayer MOT2 and in this dual gated structure. So we have both top and the bottom, they are graphite gate. The nice thing about the thin graphite is optically transparent, or at least semi-transparent, so we can pass light through it. And in these dual gated samples, we can control the carrier densities. At the same time, we can also independently apply electric field to the samples, okay? The data I show you here on the left-hand side is MCD signal intensity plot, but the zero magnetic field. This vertical axis is electric field, and the horizontal axis I show you here is the filling factor, which is the number of carriers per mole unit cells. So when the filling factor, right, is 1, means there's 1 electrons per mole unit cells. If it's a -1, means there's 1 hole per mole unit cells. Now you can see clearly, right, in the negative filling factor near -1, actually there's a finite, right, non-vanishing MCD signals. So that indicates we have a ferromagnetism in this phase space. I want to emphasize, right, this MOT2 itself is a semiconductor, it's non-magnetic, right? Just doesn't give you these magnetisms. But what we do here is actually we have a Mori system, right? We create a Mori, and with twist angle, this particular sample is about the 4 degree-ish, 3.94 degrees. So once you start to dope this Mori system at the particular carrier densities, now these magnetisms appear. So clearly, right, it's coming from strong interaction effects. So to prove we do have a ferromagnetism, so what we can do is we can park our experimental conditions at these exactly, right, 1 filling factor -1 means 1 hole per mole unit cells. Then I can measure this MCD signal as function magnetic field. Okay, right. So this field again, I sweep the field back and forth. You see a hysteresis. So the data is taken at 1.6 kelvins. It shows we do have ferromagnetisms. So we can probe this MCD signal as function temperature, right, from the bottom to the top, and increase the temperature from 1.6 Kelvin all the way to 15 kelvins. So this gives us a measurement of Curie temperature. It's about 14 Kelvin of the systems. So I just want to emphasize a little bit of this 14 Kelvin. So you may think, 14 Kelvin is low temperature, right? It's way below this room temperature. But I want to emphasize 14 Kelvin actually is a high temperature for the 2D magnetism, right? First, it's a two-dimensional system. We know that in the two-dimensional limit, magnetism usually has a really low Curie temperature. The second is that we have this filling factor is 1 hole per more unit cells. So the size of more unit cell is between 4 to 5 nanometers, which is about 10 times larger than the convention atomic unit cells, right? So in this case, the carrier densities of a memory system is at least 2 orders of magnitude smaller than these conventional magnets, okay? So with such a low carrier densities, actually we get a very robust magnetism. So my theory collaborator, Wang Yao at the Hong Kong University helped us to understand where this magnetism coming from. So what I show you here is the calculate the charge distributions in these my bilayers. And what it really shows the plot these carrier densities, right? Basically, they distribute between these two sublattice B and C, but have a certain overlap in the transition regimes. Because these wave function overlap of these carriers give rise to direct Coulomb exchange interactions and these ferromagnetism in the systems. So we can measure these ferromagnetism as function of a filling factor magnetic field. So here on the top, what I show you is the magnetic field sweep from positive to negative by continuously tuning the filling factor. And the bottom in the middle diagram, which is I sweep the magnetic field from low to high, okay? Then the difference between the top and the middle panels give rise to the hysteretic component of my ferromagnetisms, okay? This just shows that the ferromagnetic phase diagram is around from near half filling to about 1.2-ish for these particular samples. Okay, so we can also measure the Curie temperature as function filling factor. You can clearly see that the Curie temperature is highly dependent on these filling factor, right? And near optimum filling factor 1, we got the Curie temperature around 14 kelvins. When you tune these Curie filling factor away from this 1, right, you see Curie temperature really drops, and eventually magnetism vanishes. Another interesting thing what we can do with this system is this Morley system, 2D material is highly tunable. So we can show that we can really control these magnetic phenomena. So what we do here is I show you 3 curves where MCD measurements at the 3 different filling factors. The top is, at the different electric fields. The top is about 0.3 volt per nanometer. The middle is 0.15. The bottom is 0 volt per nanometer. So you can see that by tuning these magnetic fields, right, we can control these ferromagnetism. Eventually, we can actually kill these ferromagnetisms. Same, we can also tune the Curie temperature of the system just by changing this vertical electric field. So I want to talk about why we can tune these ferromagnetism just by applying these vertical, right, electric field. So the zero electric field, right, the system has these honeycomb lattice structures, right? So basically, you can think of it's a quarter field honeycomb lattice. Now, once apply electric field, what this electric field does is to actually break the degeneracy between these green dots and these orange dots. Basically, we have 2 triangle sublattice, and they form this honeycomb. But the application of this vertical electric field actually break this degeneracy between these 2 triangles, and you push all the carriers into 1 triangle or in 1 layers. So in this case, you can see the effect of this electric field basically is to tune the superlattice symmetry from these honeycomb into a triangle lattice. So a quarter field honeycomb lattice, right? To start with, once we apply electric field, it becomes a half field triangle lattice. So we know that for half field triangle lattice in a strong interaction limit, a possible ground state is a model insulator, but with these 120-degree Niels order, right? So that's one of the possibilities that we don't see any ferromagnetism in the strong electric field regimes. So the still question remains, right? I just sort of give you a hand-waving picture in the triangle lattice. You have these 120-degree New order. What's really the nature of these magnetic exchange interactions, right? In these four-layer polarized state. And then during the electric field tuning of these magnetic phase transitions, right? What's the nature of these phase transitions? So what we did here is that at the large electric field, right, as I show here, these blue dots, we apply larger electric field. Then I measure this MCD signal as function magnetic field. Then we measure it as function temperature. So from the bottom, 1.6 Kelvin, and to the top is 15 kelvins. So next, what we do is then we take derivative of this MCD signal as function magnetic field, okay, near the zero magnetic field. So this derivative can be used as a approximation to magnetic susceptibilities, chi. So then what we do is we plot these slope as function of a temperature, right? If we consider the slope is a proportional to these magnetic susceptibilities, then what we do is then we fit these, we can fit these dots to these Curie West temperatures and fit these Curie West forms, then we got these Curie West temperature, which is around -4 kelvins. And so the important point of these fitting is that tell us that the Curie West temperature actually is negative, means the magnetic interactions at a large electric field is antiferromagnetic. But we still don't know exactly, right, what's the order of these antiferromagnetism. What I'm trying to say here is we, at least from these measurements, we know the interaction is antiferromagnetic, but we don't know whether it is a 120-degree Newton's order or not. Then the other thing we can do is that we can measure this MCD signal by continuously tune this electric field. Okay, so there's two different colors here, right? One is orange, there's green. So this just means one curve is I got by sweeping electric field forward, the other is by sweeping electric field backwards. So you can see there's basically no hysteresis in this measurement. And this indicates probably this is not a first order transition, because otherwise we should see hysteresis. The other thing what we did is I can measure this slope, as I talked to, right, in previous slides, at the different electric fields. Then I plot the slope as function of electric field. You will see that the slope of these magnetic susceptibility basically reach singularities near the phase transition boundaries. So this also gives a signature that the phase transition could be continuous in such a systems. So the other interesting thing is that why, right, this MCD signal has these kind of wing-like features, okay, which is strange, right, because you can extend out to a larger electric field. So what I did, I show you here is I measure this MCD signal starting from filling factor -1, but at the large electric field. Then we continuously tune this filling factor, right, to large filling factor. So you can see that initially, right, this magnetism vanishes, then appears, then suppresses again, basically across this line. Okay? Then the question is what's going on here? So to understand this, we can start with the filling factor, the -1, at the large electric field. In this case, right, it's a half-field triangle lattice, means every these lattice sides has one carriers, right? And we know that, as I talked to you, one possible state of this half-field triangle lattice, which is a 120-degree New order in these Mach states. So on the right-hand side, what I show is the band structure, right? You know, the left shows the Mori mini bands from the bottom layer, and the top shows these Hubble band from the top from top layers. So the Fermi level is in the middle of the gap, which is the insuline state. I'm going to show you more in later, right, where we know it's insuline state. Then now imagine, right, I'm going to start to put extra carriers in the systems. Right? Initially, the filling factor is 1, right? 1 means that every Mori set on the top layer already have a 1 carriers inside, okay? Now we're going to add extra carrier in the systems. then this carrier can only have a two-way, have only two places to go, right? One is go to the top layer. So if the carrier go to the top layer, then they have to overcome these on-site equivalent yield interactions, right? Because the top layer already have field. Then the second possibility is the carrier gonna go to the bottom layer. But if the carrier go to the bottom layer, they have to overcome these charge transfer energy due to these application of the electric field, right? Then eventually, so the carrier either go to the top layer or go to the bottom layer, depends on the competition between these two energy scales. One is this on-site yield interaction, the other charge transfer energy. So in the condition when these on-site interaction energy U is larger than these charge transfer energies, then these carrier are gonna go to the bottom layer. So once the carrier go to the bottom layer, so what they're gonna do is basically they're gonna mediate the magnetic interactions between the carriers in the top layer, give rise to these ferromagnetisms. So that's why we see these ferromagnetisms actually come back once we dope the system. So I think this is actually a nice system to study, right? To study these different interaction on-site, the charge transfer, and also Coulomb interaction, etc. Okay. So I'm gonna skip these slides. So that's the first generation of the sample we have on the left-hand side. And you can already see there's a little signature of something, right, at these fraction filling, but it's not clear because the sample quality was not great. When I say sample quality, mainly in this case, is the Mori disorders, okay? And then we work on the samples and we improve it. Here's these same MCD signal measurements, but for the second generation samples. Now you can see the signal actually much, much better, right? And in such a sample, we clearly see there's a signature at the fraction filling. In this case, it's 2/3. So it indicates there's a state here at the 2/3 fillings, and the state actually spontaneously break transversal symmetries. So when we saw these data, actually give us hope that it's possible where there's a FQH effect in such a system. So this just to show how good a sample is. Now I want to show you the same measurements of MCD as function magnetic field at a different filling factor. Now you can see this curve, right? These features are just really sharp. Whenever the spin flip transition is really sharp, means the sample is kind of clean. There's a lot of domain effects. And the other feature you will see that the cohesive field, right, also has strong dependence on the filling factors. So what I can do is I just plot these the hysteretic component of my MCD signals as function filling factor. Now you can clearly see that this cohesive field is enhanced at the filling factor minus 2/3, and also enhanced at filling factor minus 1. So with zoom in, there at the near filling factor minus 2/3, actually there's small features here at the minus 3/4 fillings. And this small feature is highly position dependent. So sometimes we see it, sometimes we don't. So what it means is, well, these to actually form such a 3/4 filling state, we need a really high quality samples. And at this point, we still don't know what this state is. We know it's a ferromagnetic state, but other than that, we don't know much about it. Okay, so now I show you that we have a ferromagnetism in the system, right? This ferromagnetism is coming from the strong interactions. So next thing is we like to probe the topology of the systems. So when we first carry out these measurements, we could not do the transport because it's difficult to fabricate a high quality device with a good electrical contact. So the technique we use is we measure the strata formula of the system. So what it means is if the system, right, is a gapped topology systems, then if you measure the carrier density, right, corresponding to these gap states as function magnetic field, you will see actually a dispersed curve and a slope corresponding to the chain numbers. Okay, so just represented by this formula here, which is strata formula. So strata formula, this whole argument is based on these thermodynamic arguments. And the strata formula technique has been widely used in the community to understand the quantum Hall physics. So here I show two examples, right? One is from Amiya Jacobi's group. Right? They use SET measurements of measure the match angle twisted Bayes graphing. That's how they infer, right? You see this slope, you have this dispersed curve. That's how they infer the FCI states above 5 Teslas. And on the right-hand side, I show the results from Elliott studies group. They use STM measurements of these chain insulator, also in match angle twisted graphene. So in this case, right, they also measure these carrier density of the gap states as function magnetic field. From there, they infer the chain number of the systems. So basically, strata formula is a way to measure to extract the chain number of a quantum Hall system if we cannot do transport. Okay, so we don't have these in our lab, right? We are not doing these SET or STM measurements, but what we do here is we use optical technique. So let me just briefly walk you through of these systems. So if imagine you have a semiconductor, right? When you shine light to excite these electron-hole pairs, you're gonna get the excitons. In this case, right, it's a neutral exciton, basically electron-hole pair bound together. If we start to dope the systems, and especially in the 2D limit, means that the screening effect is weak. Therefore, these neutral exciton can bond to another charge carriers and form a trion systems. So here's an example. How can we tell these neutral exciton and a trion apart? Right, here I show you the photoluminescence spectra of a monolayer MOT2. And right, this high energy peak is a neutral exciton, and then as we double the system, we got these trions. And this just show you, right? We can measure the system by continuously tune these carrier densities. What I show you here is a luminescence intensity plot of a monolayer. At charge neutrality, we have neutral exciton, and as we double the system, we start to see these trion appears. Now I can compare these monolayer data from my twisted bilayer systems. You will see these twisted bilayer very much look like a monolayer, right? We have these neutral exciton in the charge neutralities, and then we have a trion appears as we double the system. But there's a difference, right? The difference is that you see the signal is kind of a choppy, right? There's sometimes it's bright, sometimes it's dim. So because these features actually coming from the formation of a charge order in my twisted bilayer systems. So here I just show you one of I highlight the features in the whole dope site. So I show you the PO intensities as function of a filling factor. In the vertical axis, horizontal is the energies. You can see that the luminescence intensity is suppressed at this fraction filling of -2/3, and also at the filling -1. So the suppression of the trion luminescence actually is coming from these formation of incompressible states. The key is that whenever there's a incompressible state, the Fermi surface will gap out, right? Once you gap out the Fermi surface, then the number of free carriers is reduced. But the formation of a trion requires the exciton, right, bound to a free carriers. Because the number of free carriers is reduced, then the population of a trion is reduced. A direct consequence of this suppression of trion population is the luminescence intensity will be quenched. That's exactly what we see here. So the take-home message is that we can use trion luminescence intensity as a readout of the incompressible state of the systems. Now I can just compare my luminescence signal to my MCD measurements, right? It's the same sample. You can see that whenever there's a suppression of MCD signal, you see in the magnetic signal, you see there's an enhancement. Okay, so they correlate each other really well. I'm gonna skip these slides because I see. Okay, so what we're gonna do here is we're gonna measure these PO intensities, right, at the different magnetic field, right, from 1 Tesla all the way to 4 Teslas. So what you can see that actually the carrier density corresponds to these suppressed trion luminescence, actually the shifts as function magnetic field. So this means these incompressible states has dispersion phenomena. So to quantify these dispersion curve, what we do is we spectrally integrate these PO spectra. So in this case, right, this is my integration window, for examples. So once I do this spectral integration at the spectral filling factor, okay, then I plotted the PO intensities as function filling factor, as I show you here, the zero magnetic field. You see there's a two pronounced dip. One is here, right? The other one is on this side. So this one is corresponding to filling factor -1. The other corresponds to filling factor -2/3. Next, what I do is then I measure these integrated PO intensity curve as function of magnetic field. Now we can see that there's three of these features, right? You know, this one, there's another one corresponding to 2/3, there's another one corresponding to 3/5. Okay, so these dispersion features tell us that these states indeed they are topological. So we can extract the carrier density corresponding to these dispersion features and plotted them as function of and then compare them with this expected dispersion curve from this strata formula. Okay, this is straight line here. So they match really well. So this gives us the signature that the filling factor -1, we do have this quantum anomalous state, and the filling factor -2/3 and the -3/5, we have this fractional chain insulated state. We can do a bit of analysis of such a data. For example, if I just take a derivative of my PO intensities as function of a filling factor, in addition to these -2/3, -3/5 states, we can also see another state at the -4/7 fillings. So all these states basically follow the gene sequence of fractional quantum Hall state. The difference is they could extend all the way to zero magnetic field. I'm gonna skip these slides. So I think the finish is 12:30, right? Should I stop here? Or I can stop here and then talk about the transport stuff in second lecture. Yeah. 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 Please.
Yeah, thanks for the talk. The magnetic interactions that you talked about when you extracted this revised temperature. So the antiferromagnetic exchange, is this between the same or the different Morey sublattices?
With the different Morey sublattice.
Okay, so the nearest neighbor.
Hey, Derek.
Yeah, Long Chu was reporting some discrepancy between transport measurements of Hall and the Strader formula. So how the filling factor nu is just assumed to be a linear, that's just a linear function of the gate slide voltage for the gate and matching it to integer.
Yeah. That's right.
So were there any way that you could test the transport to these systems?
Yeah. So that's the second lecture I'm going to talk about. Yeah.
Well, yeah, the claim that you could get a discrepancy between Strader and a transport measurement.
I don't know if you can discover, at least from our measurement, they actually agree with each other really well. Oh, so you're saying Long's data, which is the Strader formula, doesn't match the transport. That's why you. Yeah,
it didn't match.
that was very interesting and strange observations. Yeah. We have one sample also show that, but only one sample. I could not repeat it. But for most sample we have is that they actually match each other.
I'd be very surprised that they don't match each other. Presumably there could be some discrepancy in how you assign.
That's right. Yeah. That it is a mystery basically.
Got a whole question?
Yeah.
Yeah, very nice talk. Thank you so much. So as you showed for the RMCD data of first generation, second generation, we see the quality improvement, and you said the homogeneity is kind of the key to improvement.
Yeah.
So I was just wondering what's the key improvements like?
So basically the samples of first generation and second generation is made by different students. So I think the key is, we all know, right? If you cook the same dishes, different people, That's why some people call chef. I think that's the only procedure-wise so similar. Yeah.
That's one question.
Sorry, this is very naive, but I was just wondering if you could explain the bonding, like what drives the bonding of the prions? Like what motivates a whole bond? Can you just explain what drives the bonding, like for the formation of a trion? What like causes a neutral exciton to bind to?
Yeah. So simply just interactions basically. And you can think of that's what I was drawing here, and then you know, in a 2D limit. So you can have an electron in the middle, and then you have flanked by two holes on both sides. So that this particle actually has lower energetically, it's lower energy compared to the just charge neutral excitons.
Because of the distribution of the hole in the electron, and that allows.
I cannot hear you.
It's okay.
You can ask me. Yeah. Basically, when they bond together, there's binding energies. And the binding strength depends on a lot. For example, the dielectric environment. For example, in 3D centimeters, the trion is not stable because the dielectric constant is too large, like a gallium arsenide, for example. But in the 2D, because of the dielectric, screening effect is weak, so the trion becomes very stable.
So due to the limit of time, I think we should end up here unless Professor Xiaodong